You know, it's a crazy thought, right? How an entire sprawling ecosystem, I'm talking a huge forest or a coral reef teeming with life, can just unravel. And a lot of the time, it all starts with losing just one single species. So let's dig into that. Let's see how pulling that one single thread can make the whole tapestry fall apart. So this is the big mystery we're going to try and solve today. How on earth is it possible for one disappearance to cascade into a total system failure? It sounds kind of nuts, doesn't it? Like a skyscraper crumbling just because you took out one brick from the foundation. But as we're about to find out, it really matters which brick you pull. To really get our heads around this puzzle, we need a new way of looking at it. So we're going to use this really cool framework called Constraint Resonance Emergence Theory, or just CRET for short. Trust me, it gives us a super powerful lens to see what's actually holding an ecosystem together. Okay, so what is this CRET thing? Well, at its core, it's a theory about how all kinds of complex stuff, everything from our brains to economies to, yes, ecosystems, builds and maintains itself. It's not about just making a list of all the parts. No, it's about the web of rules, the constraints, and the constant chatter, the feedback between all those parts that keeps the whole system stable and running. Here's the big idea. An ecosystem isn't just a random collection of plants and animals living in the same place. It's what we call an emergent property. All those tiny individual interactions, a wolf hunting a deer, a bee pollinating a flower, they add up to create a larger system-level set of rules. CRET calls this a macro constraint. And this powerful overarching force then starts to govern the whole show. And this is where it gets really cool. The system literally builds itself from two directions at the same time. You've got this bottom-up flow where individual critters interact, creating bigger and bigger patterns. That's called upward amplification. But at the exact same time, the whole system itself pushes back down, kind of like gravity, and it selects which species and which behaviors are going to make it. That's downward selection. It's this constant, dynamic conversation. When those feedback loops, that conversation, are strong and in balance, the ecosystem hits a state that CRET calls resonance. The best way to think about it is like a perfectly tuned orchestra. Every single instrument, every species, is playing its part and it's all in harmony with everything else. The result is this beautiful, stable, self-sustaining symphony. That's a healthy, resonant ecosystem. Okay, so if a healthy ecosystem is like a resonant symphony, what happens when you suddenly snap a violin string? Let's get into the three main ways that CRET says this beautiful resonance gets shattered. All right, so the theory points to three main pathways to collapse. First, you can lose a keystone species. Second, you can fracture a critical partnership, a symbiosis. And third, you can break one of the fundamental circuits that keeps everything humming along in balance. Let's start with keystone loss. This is probably the one you've heard about. This is all about losing a species that has a totally outsized influence on the entire system. It's a major hub for all those constraints. When it's gone, the whole system's resonance just drops. The feedback loops get weaker, and all of a sudden, other populations that used to be stable start to drift or shrink or even just crash and burn. Next up, symbiosis fracture. This is what happens when you break a super tight, you scratch my back, I'll scratch yours kind of relationship. Think about a specific pollinator and its one special flower. CRET says they're phase-locked. So when you take away one of the partners, the special unit they formed is just gone. Instantly. And get this, the system can completely fail, even if all the other species are still there, just fine. And number 3 is breaking a circuit. You see, healthy ecosystems are built on these closed feedback loops. It's pretty simple, really. Think about it. Predators control herbivores. Herbivores eat plants, and the amount of plants around helps determine how many predators there can be. It's a closed loop. But if you take the predators out, poof, the loop is broken. That downward constraint on the herbivores vanishes. Their population explodes, they mow down all the plants, and the whole local system just collapses into chaos. So all of this is telling us something really profound. A species' importance isn't just about how many things it's connected to. CRET gives us a much deeper way to see this, and it really forces us to change how we think about what holds an ecosystem together. The old way of thinking was, well, kind of basic. You just count how many other species one species interacted with. But CRET comes along and says, nope, that's not the whole story. The real question you have to ask is, how central is that species to keeping the system's feedback loops closed? We need to measure its constraint centrality. And that brings us to the absolute core punchline of this theory. You can best predict how vulnerable a system is, not by looking at the species with the most connections, but by identifying the one that's most important for keeping those feedback loops closed. It's all about the quality and the role of the connections, not just the sheer number of them. Now, this isn't just some abstract idea for a science paper. It has massive real-world consequences. Seeing the whole system this way gives us a much, much sharper toolkit for conservation, and maybe even more importantly, for restoration. So let's look at a classic example that you've probably seen in the news, reintroducing top predators, like wolves. CRT gives us a fantastic way to understand not only why this can work like magic, but also why sometimes it can fail. So why can it work so incredibly well? Because when you bring back a top predator, you are performing a powerful act of what's called constraint amplification. You are literally reinserting that missing downward pressure on the herbivores, and in doing so, you're reclosing a broken circuit. Sometimes that one single action is enough to nudge the entire system back towards that stable, resonant, harmonious state. But, and this is a big but, CRET also tells us when this won't work. If the habitat itself has been changed too much, or if other critical species are already gone, maybe a key pollinator has vanished, then just adding a predator isn't going to be enough. The system is either too weak or just too different to respond properly, and you might even risk pushing it into a whole new kind of crash. So what's the game plan here? What does this all mean for how we actually try to help? Well, the takeaways are pretty clear. We have to start measuring the health of those feedback loops, that system resonance, not just counting how many animals are there. We've got to prioritize protecting those constraint central species. And when we do restoration, we should be thinking in terms of bundles, reintroducing groups of species that work together to rebuild those all-important closed loops. And that really leaves us with a final, and I think, pretty powerful question. This theory is telling us that vulnerability isn't just random bad luck, it's predictable. So if we can get really good at identifying the species and the relationships that are most critical for holding a system's resonance together, for keeping those key constraints locked in place, could we actually finally learn how to stop these catastrophic collapses before they ever even get started?